Did you know the moon is slowly leaving us? Every year it steals a tiny bit of our planet's energy to push itself a little farther away. It's a cosmic divorce of epic proportions, happening right over our heads while we're asleep. You can't feel it, but the process is relentless, and it's been going on for billions of years. Right now, the moon is drifting away at about 3.8 centimeters or 1.5 inches per year. That's roughly the same speed your fingernails grow. That might not sound like much, but this isn't just a story about distance. It's a story about a countdown. The moon's slow departure is a symptom of a much larger process that's fundamentally changing our planet. It's making our days longer, it could change our climate. And it marks the first nearly invisible step in a chain of events that will lead to Earth's ultimate demise. So, what happens is our planet keeps slowing down and the moon gets more and more distant. What's the final act in this planetary drama? The consequences are far more bizarre and maybe even more terrifying than you might think. Let's uncover the secret of the moon's great escape and what it means for the numbered days of planet Earth. So, why is our celestial partner ghosting us? To understand it, you have to think of the Earth-Moon relationship not as some peaceful static orbit, but as a full-on gravitational dance where energy is constantly traded. The real culprit behind the moon's escape is a force we all experience every single day: the tides. The moon's gravity doesn't just pull on Earth, it pulls unevenly. It tugs harder on the side of Earth facing it and less on the side farthest away. This differential pull stretches our planet, creating two bulges of water, one on each side. We call these tidal bulges. Now, if the Earth didn't rotate, those bulges would line up perfectly with the moon. But our planet spins, and it spins way faster than the moon orbits. This rapid spin drags the tidal bulges ahead of the moon. Now, these bulges, each containing trillions of tons of water, have their own gravitational pull. The bulge leading the moon pulls it forward, giving it a tiny gravitational kick over and over again. This kick does something remarkable. It actually accelerates the moon. But in physics, there's no such thing as a free lunch. To speed the moon up, that energy has to come from somewhere. It's stolen directly from Earth's rotational energy. The friction between the moving tides and the ocean floor acts like a giant brake, slowing our planet's spin down bit by tiny bit. Think of it like a figure skater. When a skater pulls their arms in, they spin faster. When they stretch them out, they slow down. In this cosmic ballet, Earth is the skater and the tidal bulges are its outstretched arms. By pushing the moon farther away, Earth is effectively stretching its arms out, and its rotation is slowing down. So every single day, a tiny fraction of our planet's spin gets converted into orbital energy for the moon. The result? The moon spirals outwards, 3.8 centimeters further away each year, and our day gets longer by about 2.3 milliseconds every century. It's a slow, methodical, and unstoppable theft of planetary momentum that has been going on for eons. And this has been going on for a long time. To really get a sense of the scale here, we have to rewind the clock way back to the early days of our solar system, about 4.5 billion years ago. It's thought that a planet-sized object named Theia slammed into the proto-Earth. The cataclysmic impact vaporized the intruder and a huge chunk of Earth's mantle, flinging a colossal ring of molten rock into orbit, That debris eventually came together to form our moon. Right after this violent birth, the moon was staggeringly close, maybe 10 to 20 times closer than it is today. It would have looked monstrous in our sky, a giant looming orb dominating the heavens. And the Earth it orbited was a completely different world, because so much of the system's momentum was still with our planet. Earth spun at a dizzying speed. A day wasn't 24 hours long, it was probably as short as 6 hours. The effects of a closer moon would have been profound. Tides could have been hundreds, if not thousands of times more powerful. These weren't the gentle waves we know today. They were colossal, planet-sweeping walls of water racing across the shallow oceans of a young Earth. This immense tidal friction put a powerful brake on the planet's spin, and the great energy transfer began. How do we know any of this? The evidence is literally written in stone. Scientists study ancient rock formations called tidal rhythmites. These are sedimentary layers that preserve the pattern of ancient tides, much like tree rings preserve the history of seasons. By analyzing these layers from different geological periods, we can reconstruct the Earth-Moon system from the deep past. For example, geological records from 620 million years ago show the day was about 22 hours long, and recent studies of 2.5 billion-year-old rocks in Australia have found that the moon was about 60,000 kilometers closer, and a day on Earth lasted only 17 hours. These stone archives tell us one thing loud and clear. The moon has been drifting away, and Earth's days have been getting longer for billions of years. The 24-hour day we take for granted is just a temporary snapshot in a long history of cosmic change. Okay, so we've looked at the past. But what happens if we look forward? What are the long-term consequences of this cosmic countdown? The changes are happening on geological timescales, so don't worry, you won't notice them in your lifetime. But for our planet, the long-term forecast is dramatic. First, the length of the day. While it's currently lengthening by only about 2.3 milliseconds per century, that adds up. In about 200 million years, a day on Earth will be roughly 25 hours long. That might not sound like a catastrophe, but it's just the beginning. As the moon gets farther away, its gravitational grip on our planet will weaken. This will directly impact our oceans. Tides will become smaller and smaller. Over millions of years, the difference between high and low tide will shrink, which will profoundly affect coastal ecosystems that have evolved to rely on these daily rhythms. Ocean currents, which are partly driven by tides and help regulate global weather, will also change. A world with weaker tides could be a world with a more extreme and unpredictable climate. The moon's stabilizing influence on Earth's axial tilt, the 23.5-degree tilt that gives us seasons, will also fade. The moon's gravity acts like a steadying hand, preventing this tilt from wobbling wildly. With a much more distant moon, Earth's tilt could become chaotic, potentially swinging between 0 degrees, no seasons at all, and extreme tilts that would cause catastrophic climate shifts. The predictable cycle of spring, summer, autumn, and winter could become a thing of the past. And there's one more rather poetic consequence. It's a beautiful cosmic coincidence that the sun is about 400 times larger than the moon, but also about 400 times farther away, making them appear the exact same size in our sky. This is what allows for a total solar eclipse. As the moon drifts away, its apparent size will shrink. Scientists estimate that in about 600 million years the moon will appear too small to completely block out the sun. Total solar eclipses will become impossible, a lost wonder of a bygone era, so it's pretty clear the planet we live on is anything but static. The moon's slow escape is fundamentally changing everything from the length of our day to the stability of our climate. It really makes you wonder what our world will be like in the unimaginably distant future. What do you think is the most mind-blowing consequence of the moon drifting away, the 25-hour day, the disappearing tides, or the end of total solar eclipses? Let us know your thoughts in the comments, and if you're as fascinated by the epic story of our cosmos as we are, make sure to subscribe and hit that notification bell. You won't want to miss where we're going next. This brings us to the final act. Where does this all lead? If we fast forward not just millions but billions of years, what is the final state of the Earth-Moon system? There are two potential endings to this cosmic divorce, and both paint a picture of a world that is utterly alien. Scenario A, the mutual tidal lock. Let's imagine for a moment that the Earth and Moon are left completely alone for an almost unimaginable amount of time. The Moon would continue stealing Earth's rotational energy, our planet's spin would keep slowing, and the Moon would keep drifting out. Eventually, after about 50 billion years, a new balance would be struck. It's called a mutual tidal lock. The Moon is already tidally locked to Earth. It takes the same amount of time to spin on its axis as it does to orbit us, which is why we only ever see one side of it. In a mutual tidal lock, the Earth would become tidally locked to the Moon too. Our planet's rotation would have slowed so much that one Earth day would last as long as one lunar orbit. What would that world look like? A single day would last for about 47 of our current days. For weeks at a time, one half of the planet would be scorched by the unblinking sun, while the other half would be plunged into a deep, frigid night. The Moon itself would be frozen in the sky, only visible from one hemisphere. If you lived on the Moon side, it would hang in the same spot day and night forever. If you lived on the far side, you would never see the Moon at all. It would be a planet of silent, extreme contrasts where the dynamic dance had finally ended. Scenario B, the red giant's intervention. However, there's a massive cosmic catch. The 50 billion year timeline for that tidal lock is far longer than the lifespan of our own star, so Scenario A is almost certainly not going to happen. The far more likely endgame is much more violent. In about 5 to 7 billion years, long before a mutual lock can happen, our sun will begin to die. As it runs out of hydrogen fuel in its core, it will start to swell, transforming into a red giant. Its outer layers will expand catastrophically, engulfing the inner planets. Mercury and Venus will be vaporized. The fate of Earth hangs in the balance. Some models suggest the sun's expanding atmosphere will create drag on our planet, causing its orbit to decay until it spirals into the sun. Other models suggest that as the sun loses mass, its weaker gravity will allow Earth to drift into a wider, safer orbit. But even if Earth isn't swallowed whole, it won't escape unharmed. The intense heat from the red giant will boil our oceans away completely. And without oceans, there's no more tidal friction. The entire engine driving the moon's recession would just shut down. The great cosmic divorce would be interrupted, not by reconciliation, but by the fiery death of the star that gave the system life. Earth would be left a scorched, airless, waterless rock, its long relationship with the moon frozen in time, before being either consumed by the sun or left to drift as a dead husk in the cold of space. That gentle moonlight we see in the night sky, it hides a dramatic, unending story of cosmic theft and separation. The moon is a celestial companion in the middle of a slow, silent departure, a getaway fueled by the very spin of our world. We've seen how this process began with a violent birth, how it has stretched our days from a mere 6 hours to 24, and how it will continue to shape our world's future. In the millions of years to come, our tides will weaken, our climate could become unstable, and the breathtaking spectacle of a total solar eclipse will vanish forever. And in the deep future, the Earth-Moon system faces one of two fates: a cold, silent tidal lock, or more likely a fiery obliteration when our sun goes red giant. The story of the moon's retreat is a powerful reminder that we live on a dynamic planet in an equally dynamic universe. Nothing is permanent. The ground beneath our feet and the sky above our heads are part of an evolutionary story that unfolds on scales that dwarf human existence. The moon is leaving us, and while we won't be here for the final act, its departure is the ticking clock that counts down the numbered days of our world as we know it.